Hey. All right. So we are going to discuss the concept of limiting and excess reactants. All right. So once again, imagine you're in the kitchen and you have enough bread to make 5 sandwiches, but you only have enough ham to make 3. Well, your ham is limiting you. It is being consumed. It is a reactant, and you're going to run out of it first. So we would call that your limiting reactant because it is limiting the amount of product that can be produced because it runs out first. And once it runs out, the reaction stops. We can't make any more sandwiches when we're out of ham. Okay? So let's apply that to chemical reactions. And it's really just stoichiometry, just more of it, okay? So let's look here, and here, and here, and here, and here. We'll do one practice problem, but that practice problem is going to have like 5 different answers, or 3 or 4 different answers. We'll have to see, okay? Let's get us a nice pretty color of paper so that we don't just look at this white. I'm thinking, how about a dark gray today, okay? And let's put some lines on that paper. All right, and we are getting started now. We're going to title this Limiting and Excess Reactants. One of the longest problems you'll solve all year, okay? It requires a lot of work to get the few answers that we need. First of all, the limiting reactant runs out first, causing the reaction to stop, right? And therefore determines the amount of product produced and how much of the other reactants reacted, right? It determines everything. The excess reactant is not totally consumed by the reaction, right? Therefore, some remains once the reaction has stopped. Okay? And some people like to know, how much do you have left over, right? How much do I have left over? Because I can use that. I can use that for something else. We don't need to waste it, right? So let's make up a scenario here. Let's say that we've got, let's go ahead and have our good old friend, aluminum nitrate, okay? Reacting with, maybe we will react that with, how about some sodium carbonate, okay? And what we will get is some aluminum carbonate, right? And some sodium nitrate. And I can see that this will be a 6, this will be a 2, and this will be a 3. I'm going to move that down and write my question above it so that I can write the information in up above it, because I like to do that. I'm sorry, I should have done that for you first. Let's look at our question that we're going to pose for this hypothetical reaction that is occurring. This will be a solid. Oops, that is a poor choice of colors. I do apologize. Let's make this solid. This is aqueous. This is aqueous. And this is aqueous. We are going to write a problem that says when 30.0 grams of AlNO3 reacts with 30.0 grams of Na2CO3, how many grams of aluminum carbonate will be produced. Now you need to participate in these calculations to make sure that you're getting them correct with us. You can always pause, right? I like to do the same thing every time, and I encourage you to as well. I'm going to look at my problem. I've got my balanced chemical equation. I'm going to look at my problem, and I'm going to pull out what I'm given. I'm given 30 grams of aluminum nitrate. So I'm going to write that right here. I'm given 30 grams of sodium carbonate. So I'm going to write that right here. And I am asked for grams of aluminum carbonate. So I will write that right here. And it is very obvious that we've got a stoichiometry problem because we're given information about one thing and we're asked about another. However, this stoichiometry problem is a little bit different, and hopefully you see why. And that's because we're given information about 2 reactants and not just one. We are no longer able to assume which reactant is going to run out first. So there are a few ways to solve this problem. I'm going to teach you the way that takes a little bit more time, but students tend to like it better until they learn more about chemistry. All right, so let's look at what we're going to do. We're going to say, with my 30 grams of my first reactant, how many grams of my product can I produce? And then we're going to go, and with my 30 grams of my other reactant, how many grams of my product can be produced? All right. So essentially we're in the kitchen and we're saying we have enough of this reactant to make this many cookies, and we have enough of this ingredient to make this many cookies. Let's compare our answers to determine how many cookies we'll be able to make. And that, in fact, is the approach we are going to take in solving this problem. So I'm first going to start with this 30 grams. And I actually have a lot of calculating to do. I have not been doing these types of problems because I didn't want to calculate all these molar masses, but we're going to have to. Okay, we've got 30.0 grams of aluminum nitrate, right? What are we going to do first? We're going to convert the grams of aluminum nitrate to moles of aluminum nitrate, all right? Because we need to get from one substance to the other, and we do that using our mole ratio, and we can't use our mole ratio until we have the units of moles. Remember that? So right now, I'm going to calculate the molar mass. I'm going to get my 9 oxygens. I'm going to add my 3 nitrogens, and I'm going to add my aluminum. And lucky for me, I pretty much have those memorized. So that is 213, assuming I did not make a mistake. I should do it again. Now, why did I convert my grams to moles? Well, in any stoichiometry problem, we want moles so that we can use our mole to mole ratio, moles of what we have to moles of what we need, okay? And up there, my question mark is at aluminum carbonate. So that, in fact, is what I need, all right? Now, this is my mole ratio. So I need to look at my balanced chemical equation, and I need to see that there are 2 aluminum nitrates. So I'll put a 2 on bottom, and that is for every 1 aluminum carbonate, which is right here as my product. So I'll put a 1 there. I'm going to go ahead and take this answer to grams by putting my moles of aluminum carbonate here and my grams of aluminum carbonate here. I now need to go to my periodic table and determine the molar mass of 1 mole of aluminum carbonate. For aluminum, that is 2 times 26.98. For carbon, for carbon, how many do we have? We have 3. So that's 3 times 12.01. And then for oxygen, we have 3 times 3, that's 9 times 16. All right. So what I've got here is a molar mass of 233.99. I should do that again. If I'm wrong, tell me, please. Okay, now what I'm going to do is I'm going to stop. I'm going to press equals. I'm going to solve my problem. I'm going to take 30 and multiply it by the 203.99, which is already in my calculator. So I'm just going to say times 30. I'm going to press enter. I now have 70,000 number. I'm going to divide it by, I'm going to put parentheses in my calculator, right, for the 213. So I'm going to hit divided by parentheses, 213 times 2, close parentheses. And then I'm going to hit equals. Be sure to look over there for your exponent because there is one. And I've got 16.5. And that 16.5 what? Grams of aluminum carbonate can be produced with the 30 grams of aluminum nitrate. However, I need to do this again because I've also got here, guys, I've got 30 grams of my other reactant. And what if he makes a smaller amount of products? Then I won't be able to make this 16.5 grams. So in fact, we're going to have to solve that problem. So I will now have to take my other reactants and I will have to do this again. This time, instead of having 30 grams of aluminum nitrate, I have 30 grams of sodium carbonate. That is what I need to convert to moles so that I can use my mole ratio, right? We always need to get to moles when we're doing stoichiometry because it's all about that mole ratio. So in my molar conversion, I'm going to determine the molar mass of 1 mole. So for sodium, that is 2 times 22.99. We need to add our carbon at 12.01, and we need to press equals and add our 3 oxygens at 16 apiece. So that looks like 105.99. Hopefully I didn't make a mistake there. That is for 1 mole. Why do we convert to moles? So that we can get from moles of what we have to moles of what we need. And we have the same question mark, right? We just need to know which reactant is going to run out first and limit the amount of product that we can produce. So let's look at our mole ratio. I see that I've got 3 moles of sodium carbonate. See that in your equation? So I'm going to put that right here. And that's for every 1 mole, again, of aluminum carbonate. Let me get rid of that because that's not a highlighter. So I will put that right here. Oops, change the color, my bad. I'm going to put that right here. There's my mole ratio. I'm going to go ahead and take this to grams so that I'm comparing grams to grams. And if you look up top, I'm going to write the same thing that's from our previous T chart, the very last ending, 1 mole of aluminum carbonate. We've already added this up and we've gotten 233.99 grams. So let's stop right here and do the math and then talk about what our answers tell us. So once again, we're going to take 30 multiplied by 233.99. Press enter. Now you should have another 70,000 number, same as the last time, divided by parentheses 105.99 times 3, close parentheses, equals. This time I've got 22.1. Okay, So let's look at what our answers tell us. That tells us that we have enough aluminum nitrate. You're in the kitchen. You have enough of this to make 16.5 grams. You have enough of this ingredient, your sodium carbonate, to make 22.1 grams. We now know three answers. We know our limiting reactant. So I want you to think of which reactant up there limited the amount of product produced. We know the excess reactant. So which reactant will we have some left over? We also know our theoretical yield of the aluminum carbonate. We know how much theoretically we should be able to produce if we ran a perfect experiment. Doesn't happen. Okay, so I want you to answer this for yourself. Which reactants, the aluminum nitrate or the sodium carbonate, limited our product? And hopefully you picked the aluminum nitrate because it produced the lesser amount. So our limiting reactant was in fact the aluminum nitrate. Okay. The excess reactant was our other reactant, that is your sodium carbonate. Our theoretical yield is the smaller of our two answers. It is the yield of our limiting reactant. That is 16.5 grams. Grams of what? Aluminum carbonate, Al2CO3, 3. All right. And we've got one more question. This is the hard one. How many grams of the excess reactant remain? So I know that I've got some excess of sodium carbonate, and I need to know, my employer wants to know how much is left, how much should be left. And what I can't do is just subtract, right? I need to have my initial mass minus the mass used to get the mass that remains. And this right here must be calculated using stoichiometry. Okay, there's a couple ways to go about it and you'll get the same answer, but both ways require the use of a mole ratio. So let's look up at our original equation. We know that this was limiting reactant. So we know that all of this was consumed. I'm lagging. I'm going to hold on a second. Oh, my battery's dying. Lots of problems. Okay, so look at the first reactant. That was limiting. None of that remains. None of it remains. Okay? But we know that of our 30 grams of sodium carbonate, some remains. So we need to figure out how many grams were used. Well, let's say this. We've got two options. We're going to pick this one. We're going to take our limiting reactant. This is where students get confused, but some of you guys can hang. We're going to say if 30 grams of this reacted completely, which it did, we've proven it with math, then how many grams were used? And that's your new stoichiometry problem. So we're going to go from limiting reactant to excess reactant. So everything's labeled. We don't need to calculate any molar masses. We're going to go from 30 grams, there's a little lag on my computer, of aluminum nitrate. All right, we've calculated the molar mass. Look up. It is the first T chart, 213. Okay. Get below y'all's mind. 213 grams for every 1 mole. Why are we converting our grams to moles? So that we can use our mole to mole ratio. Moles of what we have, limiting reactant, 2, to moles of what we need, excess reactant, 3. And that is sodium carbonate, okay? I need to make this a little bit smaller because I'm running out of room. Okay, and let's go like this. This was aluminum nitrate. We now need to convert the moles of sodium carbonate to grams. If you look up, we've already calculated the molar mass of sodium carbonate. It is 105.99. Okay, it's right here. Everything's labeled. It makes it really easy to find your numbers and you don't get as confused. So if you are rushing, it's not going to work, okay? You need to take your time and make it nice and neat. Nice and neat. Let's go ahead and solve our problem. This is going to give us the grams used, not what remains, how much was used. We've got a 30 times a 3 times a 105.99 equals divided by a 213 times a 2, close parentheses, equals. I've got 22.4 grams of Na2CO3 reacted. We initially had 30 grams of Na2CO3. We just determined that we used, let's label that, we just determined that we used 22.4 grams. Therefore, if we subtract, we should get what? 7.6 grams of the sodium carbonate remains. Boom. There you go. That's stoichiometry for you. Period. Done. Kahoot. Throw some solutions in there. Throw some acids and bases in there. Throw some gases in there. But this right here is stoichiometry. All right?